Good morning, or good afternoon, or even good evening, depending on where you are at. My name is Atarut Azizin Amini, the director of the IBT/ABCUTC at Florida International University. Very warm welcome to more than 800 sites that have signed to listen to our June 2024 monthly webinar live. We are delighted to have with us today three speakers, John Gay with Imperial County Public Works Director, Darab Guzar-Jomehri, Senior Project Manager with NV5, and Guy Nelson, Product Development Director with Valmont Structures. The title of the webinar today is Dogwood Bridge Replacement Utilizing Press Brake Top Girders, and I promise you it's going to be a very interesting presentation. During the registration process, we did get a number of questions that time permitted. We are going to try to get to them. This webinar will finish somewhere between 15 to 20 minutes after the hours, depending on the questions, but it is not late. If you have some additional questions, please, by all means, post them on the dashboard, and we'll try to get to them as time permitted. A couple of major announcements again. The 2024 World Bridge Engineering Conference is right around the corner. It's December 11, 12, 13, 24 in Miami, Florida. 32 states have co-sponsored the conference, including the Federal Highway Administration. We have lined up some very exciting keynote speakers that's going to deliver their talks during the Wednesday, the first day of the conference. Michael Knott on the ship collision, Shim on the exciting works that's going on in automation in the forest, and Eugene Burweiler summarizing some of the innovations going on in Europe. I'll be talking about the 3D printing. We have a Mark Fensley to tell us about artificial intelligence, that's hot topics, and of course, Ben Graybill, that always has exciting innovations that share with us. We also have John Hillman, who is the Structural Engineering Director with Kiewit Engineering, on evolution of the bridge project delivery. Frank Jolinus has done some exciting work in the foundation reuse in ABC, some very recent ones. And also we are delighted to have with us Danielle Whitlow with the U.S. Army Engineering Research and Development Center to tell us about the bridge engineering from the military standpoint. So it's going to be a very exciting series. Registration is open. Please take advantage of the early bird registration rate. The copies of all these slides are going to be on our website, but if you go to our website, you can get all the information about the conference. Registration is open. Take advantage of the early bird. You need to reserve your hotel room at a special conference rate while it's available. We also have opportunities to exhibit. There's a travel scholarship available for the U.S. state and county bridge engineers. You need to apply for it, and the application is online, very simple process. We also have on Thursday night, we have a workshop by Eugene Burweiler from Switzerland on basically design examples using a UHPC for repair retrofit of the bridges. On Wednesday night, we have our receptions, so don't miss that. So at this point, I'm going to turn it to Kathy, who's going to share with us some information and news related to the bridge engineering. Kathy, it's all yours.
Thank you, Torad, and thank you all for joining us today. Before we get started with the feature presentation, I'd like to go through some of the upcoming events in the industry. So first, we have coming up in just 2 weeks, the ASBE, American Segmental Bridge Institute, is presenting a seminar on construction practices for segmental bridge, concrete bridges. The date for that is June 27th and 28th in Denver, Colorado. On the screen, you can see links for both the registration and additional information should you have questions. Next is the 4th International Bridge Seismic Workshop. This is presented by the Canadian Association for Earthquake Engineering and Seismology and Carleton University. This event is August 11th through 14th in Ottawa, Ontario. And again, there's a link on the screen for more information and registration. In September, our colleagues in the American Composite Manufacturers Association, the ACMA, will be holding the Composites and Advanced Materials Expo, CMAX. It's September 9th through September 12th in San Diego, California. This is the Composite Manufacturer Association. This is their major event of the year. Another upcoming event is from ASBE. It's their 36th annual convention and committee meetings, October 20th through the 23rd in Atlanta, Georgia. And this is their primary event of the year, ASBE's primary event. Now I would like to do the upcoming events that are for the IBT ABC. Thursday, July 18th, we'll have our next monthly webinar. It's on a 30-span slide bridge over the Gila River in Arizona. This will be a really interesting project. We do see quite a few slides, but very few with so many spans. I believe the bridge is 1,500 feet long. It's really quite an amazing project. It will be presented by Robert Ringwald and Chris Levy from AECOM. Please mark your calendars for that event. Next is our quarterly research seminar, which will be held on July 26th. It's on a comprehensive decision support tool for ABC considering social equity. This is actually being presented by our team at Florida International University. This project is actually very closely related to some work that Connecticut DOT is doing. So really practical work tying in with the research. So please mark your calendars for that event. Next, in September, we're doing our once a yearly in-depth web training. So this is September 10th. It's from 11 to 3:15. As you can see, it's a longer time frame because what we do with the in-depth web training is really kind of delve into a single topic so we can get a lot more depth in the topic. So our presenters are Dr. Aziz Namini, Ben Graybill, Eugene Bruweiler, and Sam Falaha. The topics that we will be covering, the modules will include UHPC shotcrete, 3D printing utilizing UHPC, overlays for bridge deck rehabilitation. We'll go over some design examples, and we'll also have updates from FHWA on the structural design specification guidance and the evolution. And finally, we are to our feature presentation for today. So the presentation today is the Dogwood Bridge replacement utilizing press brake tub girders. We're joined today by John Gay from the Imperial County Public Works Director, Durab Bouzajomari, who is the Senior Project Manager with NV5, and Guy Nelson, who's the Project Development Director for Valmont Structures. As Atora mentioned earlier, there is a question box in your dashboard. If you have questions as the presentation proceeds, please feel free to add those. We will try to get to them in the question and answer session that will follow the presentation. John, thank you for joining us.
Good morning. It's good to be here today. We're excited to be able to present our project with you. Want to talk a little bit first about where we are located. We are located at the very southeastern corner of the state of California. We border Arizona to our east and the country of Mexico to our south. You can see by the green star, that's the actual project location. And it's interesting to note in our area, we're actually a cultivated desert. If you enjoy your winter greens, many of them come from the Imperial County. You can also see a red line that kind of bisects diagonally through the through our county. We actually sit at the very south end of the San Andreas Fault. We are known for our seismic activity here. And an interesting fact is I think basically 3 months after our bridge was constructed and opened, we actually had 4.0 magnitude earthquake swarm. The epicenter was 2,000 feet just west of our bridge. So we do have a lot of dynamic activity that happens here. Because we are a cultivated desert, we do have a lot of canal and drain systems. You can see in the photos attached this bridge. It crosses one of our 4 main tributary canal systems that help cultivate our area. The canals never run dry. It's a 24/7 operation in terms of they never are taken out for maintenance reasons, and so this project requires us to work in very wet environments. The Dogwood Road corridor is a main north-south corridor that crosses the Central Main Canal. That corridor is key because it ties directly into the border with Mexico. Our project at the time was declared an emergency because 3 out of the 4 main corridors that transit to the border north-south through our county were actually closed because of bridge issues. 2 of them had critical findings at the time, and Dogwood Road was closed as well. The issues for closure had to do with regards to ongoing subsidence. And you can see in this photo here the old bridge. This area was settling, and Derek will get into that in a little bit more detail. So because of the settling that was occurring, because of the water that began overlapping the deck, we declared a state of emergency, a local state of emergency, and we closed the bridge. There was a significant erosion issue too that was occurring at the abutments. Some of the complicating factors around this particular project had to do with a very high density of utilities of different types. There was a gas line that was actually attached underneath the bridge. It was a high pressure gas line that served one of our cities. Overhead power lines, telecommunication, as well as the drains and canals. The closure of Dogwood Road, as well as 2 of the main corridors that led to Mexico, created a major detour issue. And so this project became front and center very quickly. And the Imperial Irrigation District, which is the local raw water purveyor and actually power provider here, it's referenced as IID in this particular slide. They also indicated that we were not going to be able to take the canal out at any time or put any kind of intermediate supports within the canal system. And with that, I'll go ahead and I'll hand it over to Rob.
Torad, do you have the presentation?
I got it.
Yeah. Great.
Thank you, John. Good morning, everyone. As John mentioned, this project is used to be or was an emergency project. There was goals associated with this project, which I'd like to go through. We were supposed to design a single span bridge, mainly because IID, who is the irrigation district in Imperial County, did not want additional substructures built in the canal and wanted to have the water flow through here at all times. We were supposed to select a lightweight superstructure in order to be able to raise the bridge in the future, and that's because of the subsidence in the area. They wanted to minimize the bridge depth, and it's mainly because the area, as you can see, is very flat, and it would not work well if you raise the profile on this roadway. They wanted to reduce the construction time, mainly because of the emergency situation they had. The county wanted to open Dogwood Road as quick as possible to minimize the economic loss or cost to the farmers and the community in this area. And lastly, they wanted us to restore some of the erosion that was caused by migration of water adjacent to the abutments. And as part of that, they wanted us to provide a future erosion control so that doesn't occur. So let me talk about some of the project challenges. These are some of the utilities we have to deal with. SoCal Gas had, as John mentioned, had a 4-inch diameter high pressure line that's on the edge of the bridge, as you can see on the left photo here, and that one was under the water by the time we went to construction. They had to relocate that. The IID had a 92 kV transmission line that had to be moved during construction, but momentarily so they can build the bridge. And lastly, AT&T fiber optics telecommunication lines had to be undergrounded during this project in order for us to be able to remove the bridge and reinstall the new one. Now, having said that, the biggest and most important challenge in this project was the fact that the area as a whole was settling around the whole area. And I'll get into that in a little more detail. The area was settling approximately an average an inch a year. As you can see on this photo to the left, the gas line was absolutely under the water at the time this picture was taken. We also had another drainage line on the west side of the bridge that had to be relocated as well. So to give you a better understanding of what the subsidence was all about, IID or Imperial Irrigation District had kept track of all the subsidence throughout this area. To give you a kind of a feel for what the area's size is, from where you see the 150 plus 00 station all the way to 400, it's about a 4.7 miles. Where Dogwood, as you can see here, was right in the center of that whole area. And right above it, you can see the geothermal fields. There are geothermal fields in the Imperial County, although currently now the whole area is going to solar and as well as wind energy, and eventually these geothermal fields are going to go away, not soon enough though. The overall area that subsides is about a 7.2 miles here. To the right of Dogwood is, if you look at the screen, the Clark Road is to the right of that. That's station 350. That's the second bridge that was closed as an emergency situation. The graphs here, IID started keeping track of the subsidence. The red graph is between 1979 and 2012. The green one is 1979 to 2015, and the dark blue one is 1979 to 2019. As you can see, this whole area dropped almost close to 3 feet over the years. So that's a big challenge we have to deal with. And so in order for us to really meet the goals or achieve the goals that the county had, we looked at 3 different options. We looked at precast concrete girder bridge. We looked at a prefabricated steel tub girder bridge, and we also looked at post-tension superstructure. And we had to make sure that whichever option we select meets the requirements that the county had, the goals that the county had. And that would have been really making sure that the final selection had a lightweight superstructure, and it was a low depth of the structure, and can be constructed really fast. And so having gone through all of that, looked at all of these different options, we ended up using or selecting the steel tub girder bridge because it met all those requirements. And once we really selected that, we worked with Valmont who is the fabricator for the top girders. And we work with them to design the girders per the AASHTO criteria, per the design criteria shown on the screen here, for HL93 and CALTRANS P15, permit design load, and their seismic design criteria version 2. And we also wanted them to design these girders that can be lifted. So we talked to them to add additional plates on the bottom of the girders from each end in order to be able to support lifting the whole superstructure in the future. And and then we promised the county that in 20 years they can lift the superstructure, raise the abutment seats, and reinstall the superstructure in order to gain the 2 feet that will be lost in that period. And the bridge, as you can see here, also had 2 through lane, 12-foot lanes with shoulders, curb to curb 36 feet, out to out 39.6. The 8-inch deck with 2-foot 6-inch girder depths, and also we designed the abutments, and let me get into the abutments, which ended up with 6 30-inch diameter kiss piles, and we call them kiss, but they are cast in steel shell piles, as everybody knows. And so we ended up designing the abutments not only to meet the requirements, of the county, but also not only to meet 2 of the requirements, meaning regaining all the eroded areas as well as making sure that we won't get erosions, but we designed it to handle 8 new girders, and we stepped the abutments in order to make sure that we get 2% cross slopes on the road, on the cross section of the road. And we had placed staggered piles throughout this area. And as you can see here, we ended up keeping the existing abutment. It's shown in gray. And we put in or drove in the PS31 flat sheet piles behind the existing abutment, between the existing and the new abutment. And then we designed the abutment, placed it right behind the existing abutment, and drove additional Z piles on either side in order to make sure water does not migrate behind the abutment as well as at the edges and on the abutments either side. We did run into some issues with our piles. However, through construction, those were resolved. We ended up getting water into the pile, into the shells, and we changed the plug up to, I believe the final was about 10 feet of plug that caused the water to stop and not come back into the shells. So that got resolved during the construction. And now, just to mention what the consequence or what the sequence, I apologize, what the sequence was through construction. As I mentioned before, one of the utility companies, which was the gas utility company, had not relocated their line by the time we got the girders in. And we couldn't remove the deck from the bridge because they had high line, that gas line over the bridge deck. And we could not remove the whole entire bridge deck. And they had to HDD, or horizontal directional drilling, that pipe underneath the whole canal in order to relocate it. So meanwhile, we were running out of time. So the contractor came out, and as you can see here, they built mock abutments on either side, 2 mock abutments on the side of the canal. We kind of assembled and placed the girders on those abutments and formed everything, put the rebars, casted individual slabs for each of these girders, and then waited till while they were, we were waiting to get cured. The gas company finished their work. Then we went back and removed the old bridge deck. And as you can see, we left, as I mentioned, we left the substructures, including the piers, the two pier that was in the canal. And then we, one by one, moved the girders plus the precast deck back into their final location on the bridge abutments. And once we did that, we went back. And by the way, these had 8-inch space between each component. So we ended up constructing the bridge railing and pouring the deck closures, and then finally built the back wall of each abutments and went back and finalized the roadway for this project. With that, I'm going to pass it on to Guy Nelson from Valmont to give you the rest of the presentation. Thank you.
Introduce what the project, and by the way, thank you, Darab. And I did want to say about this slide, for those of you who haven't been to Imperial County or this kind of southeastern area of California, absolutely amazing that this can happen in the desert. So I wanted to say the reason I left on this slide is the innovation of this project really started 150 years ago when some engineers, surveyors, and geologists decided, hey, let's convince the United States government to reroute the Colorado River through the Imperial Valley so that we can irrigate this desert. John is not kidding you when he says this is an irrigated desert. If you ever come here, you will drive 2 hours through brown, lifeless desert and drive into this oasis. And you can see it here on these pictures. It is absolutely amazing. I just wanted to point that out. So to the project. I mentioned the innovation of that was done 150 years ago. Well, Valmont also is an innovator in the agricultural irrigation system. So Valmont started with their own center pivot irrigation system. To do that, to build that system, they required to fabricate steel. This was started in 1940, Valmont Industries. And then they built into a worldwide steel fabricator, now fabricating steel throughout the United States, and a AISC intermediate bridge certified steel fabricator that we deliver bridge products throughout the United States. And for this project, we delivered our press brake form tub girders, or like we like to call them, our U-beams. A little easier to say than press brake form tub girders. So we have 5 different shaped tub girders. As you can see here, they range in spans from our shallowest U12, which can get out to 40 feet long, all the way up to our deepest, our U33, that can span a full 100-foot long single span under AASHTO HL93 loading. So the press brake tub girder is a product brought to us by the Short Span Steel Bridge Alliance, and I'll talk about that in the rest of the project. So want to get into the specifics of, first of all, if you don't know what a press brake tub girder is, it's been around for about 20 years now. First project was installed in Monroe County, Michigan in 2004. It's been researched by Michigan State University, Iowa State University, Marshall University. So it's done a lot of research. And basically, what a press brake tub girder is, as you can see here, as Iowa State University defines it, is it's simply a flat piece of AASHTO M270 plate made in the USA, flat steel plate, bent into a structural shape. That structural shape is what AASHTO would call a steel box section. All the fabrication procedures and design follow the AASHTO bridge specifications. There have now been over 100 bridges throughout the United States installed, with this being the first installation in California. AASHTO has also recognized this product, press brake tub girder, with an AASHTO Innovation Initiative Award back in 2020, where it was deemed a ready to implement technology. We also were awarded a Focus Technology the year after. And then finally, maybe some of you have even seen, if you're familiar with press brake tub girders, back last year, Missouri DOT, Pennsylvania DOT, Michigan DOT, and myself gave an AASHTO presentation, AASHTO AII presentation about the press brake tub girder technology. So, what is a press brake tub girder and how do I design it? Well, that's a great question. And if you really want to know, I really recommend going to the Short Span Steel Bridge Alliance website. It's shortspansteelbridge.org website. At that website, you will find a 7-volume research report published by the Short Span Steel Bridge Alliance. And in that report, you'll find full-scale testing, full-scale example projects, fatigue testing, live load distribution factor verification, and complete AASHTO design procedures, which are shown here. Basically, a press brake tub girder is a term that was coined by the Short Span Steel Bridge Alliance, but basically it is a AASHTO steel box section. It's as simple as that. The NSBA, the National Steel Bridge Alliance, through AISC, will be publishing a press brake tub girder design manual. With it, Valmont will be planning to release also some design software of their own, so that you should look for that coming in the future through the NSBA Technical Resources website. So in this manual, you'll learn about how the press brake form tub girders were developed through the Short Span Steel Bridge Alliance. And as I said, there are 5 shapes, are standard, that were developed through an efficiencies study through the Short Span Steel Bridge Alliance. Why 5 shapes? Well, if you buy steel plate from the mill, there are basically 5 widths that are standard rolling widths from the mills. A 6-foot, 7-foot, 8-foot, 9-foot, and 10-foot plate. So if you can see here, the U12 is basically fabricated from a 72-inch wide steel plate all the way up to the U33, which is fabricated from that 10-foot or 120-inch wide steel plate. So we want to get as much as we can of that flat plate used into our press brake and not waste any of the steel that comes off of the mill roll. So with these 5 shapes, we have also developed what we call our beam selection chart. So with this chart, you can get some preliminary sizing. So if you're starting a job, if you're doing a study, probably what NV5 did to start this job out was to get an idea of, okay, and we highlighted here, if I'm at a 75-foot span, what sizes should I use and what spacing should I use of a press brake tub girder? So for that 75 feet, you can go with the most efficient section, which would be 33 inches deep and at 8-foot spacing, if you want the cheapest option, or if under clearance is an issue, like it was on this job, or you want to have additional hydraulic capacity underneath your bridge, you could go with the smallest beam, which is a U24 for the 75-foot span, but you'd use about twice as many beams. But depending on your situation, you might need that for your specific situation. All these beams meet in this chart, meet AASHTO loading, HL93 loading. They also meet they also meet the live load deflection requirements of L over 800 for the live load deflection requirements. You'll notice that a lot of these are actually shallower. AASHTO recommends a beam depth of minimum beam depth of about L over 30. You'll notice on this chart, a lot of these can be used at an L over 40 and still meet that live load deflection requirement, which is a reason why this product was so beneficial on this project. So getting to the specific project. So as Dara mentioned, why did they end up choosing a press brake tub girder, which had never been used before in California, and NV5 had never even designed before this project. Well, it fit a lot of the requirements that they needed for this project. First of all, they needed to span that full 90-foot width across that drainage or that irrigation canal. It's a little deceiving. The existing piers were left in place. We did not use those existing piers to support the new bridge. We had to, again, governed by the IID. So I found out through this project, the IID, as I'm from the East Coast, the IID is kind of like the railroads are on the East Coast. It's their property. They dictate what needs to be done over their property. And they said, we're gonna span the full 90-foot canal width. And they didn't want any of the contractors in their canal during construction. So it was a superstructure removal, but then we basically replaced an entire bridge around that existing substructure. Part of it also was we had to give, or NV5 had to allow for about 2 foot of freeboard underneath the bridge to the existing water elevation. As you saw from the pictures earlier, that existing bridge had already settled and was restricting flow of the canal. So we had to raise the bridge up 2 feet. We had to span 90 feet. The old spans were only 30 feet. And NV5 had to tie it into to the adjacent roadway, access roadway that were right off of the approaches. So very critical for NV5 to have a very shallow depth system. Otherwise, they would have pushed the approach work into 4 different roadways coming off of this bridge. So again, through the study, they chose the U30 press brake tub girder. So again, that U30 shape is about, again, 30 inches deep, over 90 foot long. So you're still looking at that less than L over 30 beam depth, span to depth ratio. But we need that very shallow depth to keep that raise in elevation as small as possible. You look at this also, and they could have used the U33 and maybe eliminated a beam line or 2. But as Darb said, they have settlement issues or subsidence issues. So every inch they could maintain of underclearance, every inch extra were years they could add before they needed to jack again. So it's very important to get the shallowest depth possible. So why was a press brake tub girder so effective in this situation, and why is it so effective overall? First of all, there are no welds. So as far as the fabrication of the press brake tub girder, we provide no fatigue critical details in the tension zones of the press brake tub girder. What does that mean? Basically, that means there's nothing to inspect. It's flat plate that is bent to a 5 times the thickness of the plate bend radius. You can see here on that bottom right, that picture of the different bend radiuses there. These have been tested, Sharpie V-notch tested all the way to a 1T bend radius, and found there is no loss of fatigue, or I'm sorry, no loss of toughness in that 1T bend radius. So we're very confident that AASHTO M270 grade 50 plate is going to perform very well and have no damage when we're bending it to that 5T bend radius. Also, what that does is it helps inspection. If you think about it, what are you inspecting then if you have no fatigue critical details in tension zones? Well, really, you're just looking at the thickness of that plate. And if the thickness of the plate is all you're concerned with, well, then a very durable coating system is what you really want. And that's what Imperial County chose for this project. They chose to use a hot dip galvanized coating rather than they could have chosen to use a weathering steel system, an uncoated weathering steel. They could have chose a 3-coat paint system, but they chose galvanizing. Why? As you saw those pictures that Darb showed earlier, it'd be very difficult to come back and do any kind of maintenance to these beams with that very shallow underclearance to the water level. So they wanted a product that would, a coating that would last a very long time, maintenance free. And that's what galvanizing gives you. So there is a project here, I'm out of Michigan. There is a project here locally in Michigan that was galvanized back in 1966. We went back out. Valmont is also a coatings company. We also galvanize. We went back out and inspected that bridge just a few years ago. It's 60 years old. We determined that the coating left on that, 60 years old, no maintenance to that existing bridge. We determined that that bridge had enough coating thickness on it, I think it was 2.7 mils still left, that we had another 40 years of maintenance-free service life on that bridge. Again, galvanizing has been proven to be a very long, durable, maintenance-free coating protection. And that's why Imperial County chose it for this project. So we get into the fabrication of these beams. So we've got the order from the county. MV5 chose to use press brake tub girders. It went out for bid, and Valmont was chosen to provide the press brake tub girders to the county. So Valmont produces our beams in Jasper, Tennessee. So one might think, Jasper, Tennessee, why? How could it be economical to bring beams all the way from Tennessee to California? I just want to remind everybody that for the AASHTO M270 plate or M270 steel, most of that is built right here in the Rust Belt of the United States. So one way or another, the steel that gets to California is coming from these three sources, either SSAB out of Iowa, Nucor, who has a few plants, SSAB is out of Alabama and Iowa. Nucor has a brand new plant in Brandenburg, Kentucky, and one in Alabama. And then Cleveland Cliffs, who are out of, I think, Pittsburgh, Pennsylvania, and Nucor is also out of Hartford. So that steel is coming from one of those sources one way or another. And what we found, we can ship as many as 6 press brake tub girders after they are fully fabricated on a standard size trailer anywhere we want without any permits. They're not overweight, they're not oversized. Whereas if you're shipping around that flat plate, if you think about it, we produce it out of flat plate that is up to 10 foot wide, costs a lot more money, especially on these U33s that required a 9 foot wide flat plate. A lot more efficient to ship the flat plate to a close location where we can fabricate it and then ship the fabricated tub girders to the final delivery. I also wanted to mention that these beams being 90 feet long, there are not press brakes that are 90 feet long. So you have to fabricate them in pieces. The longest Valmont can do, there are many press brake, many companies out there, fabricators out there with press brakes. The longest press brake we have is a 60 foot long press brake that yields a 58 foot long single piece. So for this particular situation, this single span application, we fabricated each beam assembly in 3 pieces. The main girder piece, the middle span, the middle piece, that was, I think it was around 55 feet long, and then 17 and a half or 17 and a half, 20 and 20 to make up the difference. So you don't want to put the splice, I think all you structurals out there know, you don't want to put the bolted splice right in the middle of the span. You want to put it as close to the supports as you can to reduce that moment. So these beams, these 8 beams were all required 3 beam pieces. So we delivered 24 press brake tub girders to the job site. We delivered these jobs. Press brake tub girders can be built. Tub girders can be built very quickly. These jobs were delivered about 12 weeks after we received the purchase order. We actually delivered these beams prior to the contractor mobilizing to the job site. Once the contractor mobilized to the job site, they found that the gas main that John talked about earlier had not been relocated yet. So there was about a 4-week delay due to the utility relocation on this project. So one of the things that the contractor came up innovatively was, rather than waiting around, this bridge was designed as a single span with a cast in place concrete bridge deck. So rather than waiting around for the utilities to be relocated so that then they could start demo. As you saw earlier in Darab's photos, they set up a staging area on site and actually precast the concrete deck prior to lifting them in place. So basically, they changed this project from a normal project to an ABC project during the project, which is pretty innovative in itself. The contractor chose to redesign these beams through Valmont. They asked Valmont if that was possible, and with the help of NV5, they redesigned the beams to be a PBU units type installation, and basically got back the 4 weeks through ABC construction that they lost for the utility relocation. So another one of the aspects that made press brake tub girders the choice for NV5 was the future jacking of this product, or of this superstructure product. So if you see here, there were jacking plates that were installed about 10 feet from the abutments. In the future, as you can see, there's existing piers and the abutments that were left in the canal. Those existing abutments will actually be, you can kind of see the little speck there on that picture on the upper right. That jacking plate was positioned right above the existing abutment so that they could jack off the existing abutment in about 20 years, when they anticipated that that bridge would then subside down into the canal again. So why was that so critical for press brake tub girders, or really just steel in general? If you think about a pre-stressed concrete beam or a post-tension concrete slab, you would have to do the pre-stressing, post-tensioning for the full 90-foot span, but you'd also have to make sure it would work for the jacked span of about 70 feet, which plays with your top and bottom concrete stresses. With the press brake tub girders, we simply put a jacking plate underneath the beam. We put as you can see here, we put a bearing diaphragm right above that sole plate to jack up, and then we also positioned a inspection hatch port right between the bearing plate, internal bearing plate, and the splice, the bolted splice, so that in the future you could easily look inside of your beam and make sure there's no deterioration happening around those splices or at your bearing stiffener. And then again, the things that came up that we didn't know about is a benefit to the versatility of a press brake tub girder. So basically, on the fly, the contractor, working very closely with the county, NV5, and Valmont, the contractor changed this around, as you can see the staging area, from being a cast-in-place bridge that is shown in that upper left picture. They changed it and basically cast that, precast those concretes in place on the job site, and then lifted them into place. And then NV5 actually designed that 9-inch wide closure pour that used standard CALTRANS concrete in that closure pour. So very innovative design. It took the whole team to do this. Again, I want to give kudos to everybody involved with this, because there was a lot of things that were moving on the fly to make this project a success. So what else in California has been done since the installation of this? Well, about 6 months later, we then installed another bridge, basically a mirror image or a exact duplicate of the Dogwood Road Bridge was installed about a half-mile down canal on Clark Road. So you can see here, that one was actually done with a cast-in-place bridge deck. The same contractors that installed that first bridge also were awarded this project, and instead of doing it the precast way, they did it with the as-designed cast-in-place method. Additionally, the bottom you can see, we did a project in Chico, California, where press brake tub girders were fitted up in the field with full-depth concrete, precast concrete panels, and then grouted in the field to make them composite, and then the whole thing overlaid with an epoxy overlay after the grout cured. And then what's in the future? What does the future hold? CALTRANS is looking at doing 2 bridge replacements on US 99. We're expected to do 1 this year, 1 next year. Utilizing PBU units and precast foundations, they want to replace these 2 bridges in a week closure only. So again, a very cool. Hopefully, we'll be able to do a presentation in the future on that future ABC project with CALTRANS. And lastly, I wanted to mention the Dogwood Road Bridge received a outstanding construction engineering award through ASCE San Diego, and we received those awards just earlier this summer. And then we also are receiving an award from the Association of APWA, the Association of Public Works, or American Public Works Association, for that same project. So a very lot has been done, and it all is due to the team of all 5 of us, the 2 contractors, Valmont, MV5, and the county, all working together to make this successful. So with that, I'd like to hand it back off to John.
Thank you, Guy. We are very appreciative of being able to present our project today. It was a very rewarding project. Actually, half of my team is getting the APWA award today. So we look forward to your questions, and we thank you for the ability to be able to showcase this project.
All right, thank you for interesting presentation. Thank you, John, Darab, and Guy. So at this point, we are going to turn it to Paul Lives and Rick Liptek to moderate the question and answer period. Paul?
Okay, thank you, Torrid. Yes, we have a bunch of questions, and we'll go ahead and get with them. Let's see if we can get everyone's camera on, Rob and John. The questions, I'll start off with the questions that came in earlier. The first one I have is, what is the length for a single span press brake tub girder? And you talked about those. This one was 90 feet.
Yep, so we talked about that a little bit. So we can go, efficiently go about as short as 30-foot spans with our U12, go all the way up with HL93 loading up to that 100-foot span. I also want to mention this project required the permit loading of the California P15 truck. We had to design that in the design stage. That's a 500,000 pound truck with dual axles of 54,000 pounds. So we can handle big loads, and we can go out to about 100-foot spans.
Okay. Then what was the maximum span you could use without splicing the girder?
Yep. So there's a lot of fabricators that can fabricate these. Valmont is not the only fabricator, but Valmont has the limitation of 58 feet. Why 58 feet? Because that's what our press brake can do, but also we're a coatings company. So that is also our largest tank that we can actually do hot dip galvanizing in.
Okay. Is there camber in the press brake tub girders for this bridge?
Absolutely. And that was one of the things that came up, and Dara might be able to answer this, is when they switched the design from cast in place over the canal to precast fully supported, we had to look at, well, what are the changes to the beams were already fabricated, and we already had the camber in it based on a cast in place dead load on top of the beam. Whereas we had to then investigate and go, well, how much is that camber going to change if the contractor actually precast it on? And we gave those numbers to Darab and NV5, and they evaluated them and determined, yes, those still meet the tolerances for what we can withstand for that, for the profile of the roadway.
Okay. How do you get the camber in there? Do you bend it, or do you maybe do it at the 3 splices?
Nope, we do it with a, we invested a lot of money into a rolling process. So most of you out there know beams can be done, can be cambered in 2 different methods, either a heat cambering method or a rolling, cold rolling process. We actually, many fabricators have them for I-beams. We actually have a cold rolling process for press brake tub girders to put in the camber for the beams.
Okay. Was a continuous or continuous for live load considered for this bridge? You said you were not allowed to put the bents in the middle, so
Yeah, so it is deceiving because when you see it, it looks as though it's a 3-span bridge because we left the piers in the canal, but those piers were actually spanned over, so it's a simple span bridge in this case. But I want to say yes, press brake tub girders can be designed for simple span for live load. I'm sorry, simple span for dead load, continuous for live load. Press brake tub girders are not well equipped for true continuous beams because they have such small top flanges. That negative moment is not, you can't design for that negative moment. But so basically everything is designed. If you have multiple spans, you design it as simple for dead load, continuous for live load, and provide a link slab or something to carry that moment with the concrete.
okay. That was the next question, actually. So we'll go on to the next one after that. Who produces the design calculations and computations and contract plans for the girders?
Yeah, I don't want to answer them all, Darrell. I can let some of
Yeah,
them.
go ahead. Yeah, I think Valmont did that. We designed the substructure, and Valmont did the whole entire superstructure. We all were involved in all of the design, and I should mention that, and I failed to say that when I was speaking. I think in my almost 40 years of business, being in this business, this project was one of the best examples of collaboration, coordination, and cooperations among the owner, designer, fabricator, CM, and contractor. That's what really contributed to all this changes in the fly and the super success of this project. Anyhow, that's just my observation of this contract anyway, as a whole. But the designs were done, to respond to your question, the design for the superstructure was fully done by Valmont, and we reviewed all of that as part of the review.
Okay. Do the bends and the plate bend reduce the fatigue life of the tub girder?
Not as far as we know with the testing that's been done. Again, AASHTO has their requirements of a 5T bend radius. Actually, you know, if you go to AISC lets you bend to a 2.5T bend radius. So AASHTOs are double that of AISC. The Short Span Steel Bridge Alliance did fatigue testing for a 75-year fatigue life at I think it was around 800 ADT. SSSBA now, Short Span Steel Bridge, they are redoing that fatigue testing for an infinite design life of, I think, 75 years with like 2.5 million cycles. And that's currently ongoing at University of West Virginia. So as far as we know, no loss of fatigue with bending.
Okay. Fatigue testing for tub girders previously did not include splices. How would splices be handled for a project like this?
Splices are handled per AASHTO. So it's just steel and it's bolts and cover plates. So basically, we design splices for the requirements, whether it's fatigue or strength, the requirements of AASHTO, because in a sense, that splice is no different than an I-beam splice. And there's been a lot of research done about bolted splices.
Okay, normally you wouldn't put a bolted splice out in the middle of the span, a simple
That's
span.
correct, and we did, right, we did,
Okay.
yeah.
All right, you wouldn't do that, okay.
No, you
okay.
could, you'd have to put a really big one out there. You wouldn't want to do that.
Okay. Are steel press brake tub girders bridges fracture critical?
That's a loaded question. They are if you design them fracture critical. So there's been a lot of testing done on this, or a lot of research done on this with University of Texas and FHWA, and they've determined that if, again, a press brake tub girder is simply a steel box section. It's a trapezoidal box. And what has been determined is a steel box section, as long as you have 3 tubs, you are not fracture critical, or you are not a non-redundant system. If you have 3, now if you have 2, you can make it, you can design it to be a redundant system, but you have to make sure that if you lose one beam, the other one picks up the load, and that can all be researched and read about with University of Texas's research on basically redundancies of, and it's not press brake tub girders, redundancies of steel box sections.
Okay, there's a few other questions. These are some new ones that came in. First of all, are these girders proprietary to Valmont? You mentioned there are other fabricators.
Correct. No, these are developed by the Short Span Steel Bridge Alliance. We have our own proprietary designs, proprietary fabrication processes, but no, the press brake tub girder in general is anybody can fabricate them, anybody can design them.
Okay. Here's an interesting one on your substructure. It says, did you consider down drag on the piles due to the additional subsidence? And are the piles driven to point bearing on the bedrock, or are they just in deep strata?
Yes, so I wanted to also mention that those piles were designed for the future dead load of raising the abutment. So yes, down drag was calculated in that, but we were not, we could not drive them all the way down to the bedrock. However, they were pretty deep. They were super deep, and when I say pretty deep, they were 70-some feet deep, where the gas company had to come back and HDD their line at least 10 feet below what our piles were, in order to, because as I mentioned, our abutments went in, and the gas company, because they were late, they had to follow our design and make sure that the horizontal direction of drilling would be below the tip elevation of our piles.
Okay. By increasing the depth of the girder, is it possible to go for a longer span?
We have some things we can do to make spans longer, and yes, obviously, increased depth goes out longer. I showed the slide at the beginning that shows relatively, a U12 makes it about 40 feet. I want to stress this is a lot of times what controls, Dr. Barth is a professor at University of West Virginia. He calls these beams extremely stout and strong. Usually what controls the design is the live load deflection requirements. So yes, strength-wise, we can go longer, but the problem is with that 120-inch wide plate, currently the biggest U-beam that can be fabricated is only 33 inches deep. So unfortunately, with that 33 inches, that's pretty much all we can get out to without exceeding the live load deflection requirements.
Okay.
If you want a bouncy bridge, you can go as long as you want.
There's a question that came in that said several press brake tub girder systems were funded in Nebraska. And I was curious about what lessons were learned from constructing those bridges in the Midwest. Do you have any information on that?
No, we did one. I know we did one, and lessons learned are, no different than on these. It's always what I do in my job is I'm going out to every first project. Usually it's the first time a designer has designed them, and it's the first time a contractor has installed them. So lessons learned are new. I had a gentleman tell me one time, every issue has been done, but every contractor hasn't made every issue. You know what I mean? Is every time it's a new contractor and they've got to learn it again. Although they learn quickly, these are very similar to concrete box beams. There's no fabrication in the field. You basically just lift them, set them, and put your deck on them. So really no lessons learned except the individuals that are learning it as they go.
Okay, here's a question. Let's see. This is, you used the term OG and FG, and someone was curious what that stood for.
FG is finished grade. OG is the original grade.
Okay. Could this system be used for a multi-span continuous bridge? I think you answered that one. You could.
Yeah. Simple for dead, continuous for live.
Okay. Here's a question about what about possibly using it with stainless steel? And is there any way water can get in the tub girder and rust it from the inside out? I know you galvanized it inside and out, so that's probably pretty good. What about the stainless steel question?
Yeah, if you got the money, we can buy the steel. So I mean, I think everybody out there knows stainless steel is probably 5 times the cost of standard 707 grade 50. So yeah, absolutely, I think it would be a fantastic product in the end. But we feel galvanizing, you get, as I had a county engineer say, get you the best bang for your buck.
Okay. Diaphragm wells were inside the tub. Are these wells inspected with consideration of fatigue loading?
Well, they're inspected with consideration of what's required through AWSD 1.5 fabrication requirements. I mean, I don't know what that means, inspected with consideration for fatigue. Everything is done with consideration for fatigue and to make sure we do a very good product at our plant. However, I want to make sure you knew, I mean, those diaphragms really only went in 10 feet from the ends of the beams. Again, yeah, is there stress in the bottom? Yeah, but extremely low. Okay. So out in the middle of the beam, there are no diaphragms that go down below the neutral axis. So again, we try to not have any welds in tension zones.
Okay, the question came in regarding construction beforehand. Are there any issues with mounting screed rails on fascia beams? You girded, you did those on the land and then put them up. But if you were doing them, usually you got to make sure that you don't have differential deflection, I guess, between the interior and the exteriors.
Nope, and that they're absolutely right. Is we've got to watch our spacing of the exterior beams. You know, when you're in an open tub section before concrete is cast and it's closed, those can be critical as far as the torsion. You need to make sure torsionally and global stability. And so you have to go through all the calculations for construction loads. But no, in general, we provide in the shop, we provide studs that the screed rail can be attached to. And then basically those can be usually they're on the outside flange of the fascia beam. Sometimes they're on the inside flange of the fascia beam if the barrier reinforcement is the way. But no, we found no, and they were designed during construction for those loads of the screed rails. So we found no issues with that.
Yeah, we have one more question, then I'm going to go ahead and turn it over to Rick because we still got a lot of questions coming in. The last one I have is how do they compare to conventional construction costs, or what was the construction cost on the project?
From what we're seeing, you know, the actual construction, the overall construction cost for this project, and that included, you know, $1.3 million just in utility relocates, 6.3 million. That was the overall construction cost. The bridge itself, you know, when it came in, I'll never forget, it came in on 8 trucks. It was a wonderful sight to see. I think the bridge and all of its parts, 340,000, and that's what it was. So.
Okay, Rick, we're it's just a little bit of time left. I'm gonna go ahead and turn it over to you, and there's still a lot of questions here. Rick, go ahead.
Thanks, Paul. I'm not going to turn my camera on because I'm in a low coverage area here, but one of the questions that I see here is, can cover plates be added to the bottom to you know, get you more strength?
Absolutely, and that depends on the state. Some states do not allow cover plates. So if your state allows cover plates, we can do cover plates. So we have done those depending on the state DOT allowance for cover plates. And absolutely, it gets you longer spans, more strength. So yes, that can be.
Question about, was buoyancy considered during design, since the look appears that the water surface could come up against the bottom of the bridge or up into the bridge, I guess. So was there any kind of uplift concerns, or is that not really an issue?
I think if you looked at the high water surface elevation of those canals before it hits the bottom of the girder, it would be most likely, unless, you know, over the years it will do, but initially that 2 feet of freeboard was there and was not going to allow water to get into the girder, nor would cause any kind of buoyancy for the girder. However, over 20 years, when this area subsides, and as you saw in some of the photos, that the whole superstructure will sit pretty much in the water at that point. That's when we, and to answer your question, yes, I think we've looked at that. However, I think before that happens, that the county will be moving that whole bridge up.
Okay. Yep. So typical stay-in-place form construction now is, in a lot of places, it sounds like from this individual, they weld the support angles to the flange. And I guess in this situation with using this product, how is the stay-in-place forms kept in place?
So very simple. No welding angles. You basically, the beams are designed for dead load deflection, and then also to be cambered for dead load deflection and the vertical profile of the roadway. Per AWSD 1.5, we have to meet, every fabricator that does these has to meet the tolerances, which depending on the span, there's an equation for it, but you're talking about 3/16 of an inch tolerance, plus or minus 3/16 tolerance. So in a sense, the tolerance is so tight on the camber that you just set the metal deck directly on top of the beams, and you use self-tapping screws right on top of the beams. The contractors, that's one of the things the contractors are amazed with. The forming goes absolutely fast. You set the beams, within a day, you set all your forming, and off you go setting your rebar.
Okay. Kind of another interesting question that I see here. Has this press brake girders been considered for railway use for supporting an E80?
Yes, we definitely want to talk to railroads. Then you get into railroads and what they use for their support of the ballast, whether it's concrete or whether it's a steel plate. As I mentioned, these beams, I think everybody knows this or can tell this, is these beams rely on that composite action with the concrete. That gives them the strength. Well, if you don't have that concrete deck, if you use a steel plate deck, you don't get as much strength out of it. So we've done both ways. We look at railroads where they use a steel plate for the ballast support, and where they use concrete for a ballast support. So those things are in the works, and you're absolutely right. The U33, I think we looked at without the concrete composite, the maximum a U33 can span with 80 loading is about 40 feet. So you lose a lot of capacity, and then you have that huge E80 train load on it. So it has been looked at.
So one last question here, real quick, probably. In one of the pictures you showed, Guy, you had access hole, where you can kind of look up in the girders. Was any stiffeners required around that, any of the openings or penetrations that are put in the bottom or the sides or anything?
Nope. So we design it. Again, that opening that's one of the reasons we keep it small, is because we design it for the shear at that point, and we keep it near the end. So it did not require any kind of reinforcement. It has, you didn't see them in the pictures, it has a cover plate that fits on the inside and swivels. So it can be easily swiveled. A nut basically comes out from the bottom, and then you swivel it, and you can basically peek up inside of it. They're all too small really to enter anyway, but you can get inside there. If you open both hatches, the light will come in. You can shine the light from one end, and you can see right down the pristine galvanized interior.
Okay. Well, great project, guys, and really good presentation. I guess we could turn it back over to Adirad, and he can wrap things up here.
All right. Thank you. Thanks to our speakers and the moderators. It was a great presentation. So on that note, we will conclude our webinar today and hope to have you with us back again next month. So long.